Let's imagine we have a horizontal frictionless surface and we launch an object of mass m at a speed v naught, and so it travels at that same speed. There's no friction, can't be slowed down, and then it goes up an inclined plane of angle phi, and we want to know how far up it goes. So it'll go up, it'll slow down, and eventually it'll stop. What is that distance x, say, that it travels? There's no friction on any of these surfaces. So why does it slow down here? Well, because there's gravity that's working against it and slowing it down. So the object comes to here with a speed v naught, and then it starts to slow down. So its speed is given by a kinematic equation, which is v naught, right? So its direction changes, it's going up this way. Initially the speed is v naught, immediately starts to slow down, and it slows down by a term that looks like that. So we have to figure out what this acceleration is. But ultimately what we want is this distance x, and that's the first kinematic equation. So if we call the distance it travels here x, then that's equal to x naught, or maybe we could call this is x naught and make it 0, or we can just say what we're looking for is x minus x naught, where that's x naught. And so this is really, maybe we should write this as x minus x naught. What is that distance? That's the starting point. So x minus x naught is equal to the initial speed, v naught, but we immediately have an unknown, the time it takes to reach that point, plus 1/2 at squared, because there's a constant acceleration. It's actually a negative acceleration due to gravity, so we have to figure that out. So maybe the first thing to do is to put in things that we know here and see what we need. So we don't have the time, we clearly need that. What's the acceleration? We could do a free body diagram. Well, let's do the free body diagram. When the object is on the inclined plane, then we have a normal force here. We have an mg cosine of phi here, and we have an mg sine of phi that way. And so on the tilted axes, on the tilted horizontal component, or tilted x component, we have that m times ax is equal to minus mg sine of phi, and so the ax, so again, we should label this as ax. That is equal to minus g sine of phi. And so we have minus g sine phi over 2 t squared. We clearly need the time to find this distance, and that forces us to the second kinematic equation, which is where we started. The object reaches that maximum distance when v is 0. It starts with v naught. We know what that is. That's minus g sine of phi. And so we can solve for the unknown time, which becomes t equals v naught over g sine of phi. And so the distance traveled from the bottom of the incline, x naught, is v naught times v naught over g sine of phi. minus g sine of phi over 2 times v naught over g sine of phi squared, which is v naught squared over 2 sine of phi. Sorry, I missed the g here. So it's v naught squared over 2 g sine of phi.